Greetings everyone, welcome to Economics course, and today's lesson I'm going to talk about kinetic molecular theory of gas. So who created or who published the idea of the kinetic molecular theory of gas? Well, in 1860, two scientists, James Maxwell and Rudolf Clausius, two scientists that published the idea of the kinetic molecular theory of gas. But of course, it started by Rudolf Clausius. Then James Maxwell just added some stuff on the idea of the kinetic molecular theory of gas. Alright, so it was all in 1860. Alright, so when we talk about the kinetic molecular theory of gas, we heard the word kinetic. What does that mean? Well, it came from the word kinetic energy, or the energy of motion. So if we take an example, here you have two atoms. One is moving so fast and one is moving slowly. So which one of those have high kinetic energy? You're right, the ones that is moving faster, because as you said, the kinetic energy is the energy of motion. So the faster the object is, the more kinetic energy it has, and the slower it is, the low kinetic energy it has. All right, so we can look at that in a diagram. Also, demonstrating the phases. We can just brush up our memory with the idea of the phases. We can ignore the fourth phase, which is plasma, and we're going to take the three most famous and talk about them. Alright, so we have solids. Solids, as you can see, their atoms are tightened up and they're together. Now, of course, they do have kinetic energy. Sometimes the books of schools say that they don't have solids don't have kinetic energy, or they don't move, but that's wrong. They shiver, so they have a little bit of kinetic energy. If we go, so they have tiny space, they're shivering on in their place. Then we go to liquids. Liquids are shifting from each other, and there's movement between them, but not that freely. And they have kinetic energy higher than the solids, but not higher than the gases, the big boss. So when we look at gases, we can see that we covered the box here just to not let the atoms leave the box. Alright, so we can see demonstrating from the arrows that they're moving and bumping and bouncing around and moving randomly and hitting the walls and moving around. That shows that there's high kinetic energy and that they occupy the space, all of it, but there's distance between them. There's an empty space, but they're still occupying the container. That's why if you fill up a balloon, if you put a balloon and you fill it up with gas, it directly blows, or it gets bigger, because the atoms or the particles, molecules of air, are just hitting the walls of that container. So the particles and the elements, or the particles of air, are just hitting the boundaries or the walls of the container. Alright, so before we talk about the idea or the theory itself, we need to understand why did scientists make the kinetic molecular theory of gas? Well, they made that theory just to understand the gases and to understand them more. So the word ideal gas, I think most of students of chemistry heard the word ideal gas, but what does that stand for? Well, simply, an ideal gas is the gas that follows every certain rule of a kinetic molecular theory of gas. So the rules of kinetic molecular theory of gas are followed by the ideal gases, which are the gases that follow each rule of the K and T. What is K and T? Simply abbreviation of kinetic molecular theory of gas, KMT. I like to put the G to show the gas, but it's KMT. Alright, so we refer to as ideal gas as the perfect gas that follows the rules, but it's hard to find anything that follows the rules in life. So the word ideal comes from the word like perfect. So you can say that we have an example of an ideal student or an ideal citizen, but it's hard to find them. Especially also gases, it's hard to find an ideal gas that they follow all the rules of the ideal gas law, the kinetic molecular theory of gas. Alright, so now let's talk about the rules of the kinetic molecular theory of gas, and we're going to show it in the second board. Alright, so this is the part about only introduction and idea about the law. Alright, now let's talk about the rules of the kinetic molecular theory of gas. It has 5 rules, and I want to just put the paper next to you just to write them down, because there are 5 rules and they're a bit long. Alright, so before we continue, I just want you to understand that it's not easy to memorize it, but I made a way that it can help everyone understand it. Which is this sentence: Sarah's mother cannot find Karen. But why is that? Because each first letter of each word has a symbol for the rules. Alright, we'll talk about it right now. So let's start with Saras. It starts with an S. But why S? S resembles size. Because the first rule of the kinetic molecular theory of gas says that, I would like to write it down, that gases consist of small particles that are far apart relative to their size. Gases consist of small particles that are far apart relative to their size. What does that mean? It means that gases are made of small particles. It can be either elements or molecules, and that when they're in a container or when they're in a place, in a selected place, there is big distance between the atoms or the molecules of gas that are moving. So they're not tied up like solids, or they're not sliding away like water, like liquids, but they're like gases have empty space and they're moving freely around. So that there's big size, or there's a relative big emptiness in between them. Alright, so that resembles size. We can tell that there's small particles that resemble size, their size also, so that means size. Alright, let's go for mother. So M resembles motion. So the second rule says that gas particles are constantly in motion, or are in random motion. The moving particles are constantly colliding within each other and within the walls of the container. So the second rule says that gas particles are in constant random motion. So gas particles are in constant random motion. The moving particles are constantly colliding with each other and with the walls of the container. Alright, so does that mean? It means that gas particles are always moving. You cannot just find a gas particle that's standing or shivering only. Of course, depends on the temperature, but you cannot find it like in an outdoor temperature for 24 Celsius degree or degrees Celsius. Alright, so that shows that gas particles should always be in constant random motion. Alright, but temperature can affect the motion of that particle. Alright, so let's talk about now collision, which is cannot, the letter C. Alright, so the rule says that collisions between gas particles and the walls of the container are elastic collision. What does that mean? Again, collisions between gas particles and container walls are elastic collisions. That means that the collisions that are happening between gas particles, alright, when we're saying particles, remember that we're not only talking about the element, but we're talking about also molecules of gas. Alright, so there's collisions between them, but it's considered as an elastic collision. What is an elastic collision? An elastic collision is a collision that keeps the kinetic energy of an object. So that means if that pen is hitting the board, it's reflecting back. So why is it reflecting back? Because it still has that kinetic energy in it. So when it's moving with kinetic energy, hits the wall and reflects back, it still has that kinetic energy. It still has kinetic energy. So it has an elastic collision. So that means when they're hitting, they're not just hitting like this, and they're smashing and sliding down or just dropping dramatically. Right? No, it's like a tennis ball. When you chuck it on the board, what happens is that it reflects. Alright. So you saw that kinetic energy. It moved it a little bit, but then it dropped. So there is that elastic collision. Alright, now let's go for the word F, or for the letter F, for the word find. Alright, so here it's the fourth rule. What does it say, or what does it say? It's that there are no forces of attraction, no repulsion between gas particles. Alright, so there are no forces of attraction or repulsion between gas particles. What does that mean? It means that when a gas particle and a gas particle are moving, they're like this. For example, that's a gas particle and that's a gas particle. They're moving, they won't suddenly attract or come to each other. And if they're, for example, sliding next to each other or moving next to each other, they won't just repel each other away or push each other away. So that shows that there is no forces of attraction or repulsion between gas particles. The fifth rule talks about the kinetic energy. So that says that the average kinetic energy of a gas particle is determined by the temperature of the gas. What does that mean? Again, the average kinetic energy, abbreviated as average as AVG and K dot E as kinetic energy of a gas particles, depends on the temperature of the gas. So again, that the average kinetic energy of a gas particle depends on the temperature of the gas. Alright, so what does that mean? It means that the hotter the gas particle is, the hotter the gas particle is, the faster it's going to move. So the faster or the more to have kinetic energy, and the colder it is, the slower or the least kinetic energy it will have, or to get less kinetic energy. Alright, so that's all about the rules of the kinetic molecular theory of gas, which are 5 rules. Just remember that you have 5 fingers, and remember the word Sarah's mother cannot find Karen, and each letter resembles the main idea of that rule. S for size, M for motion, C for collision, F for force, kinetic, K as kinetic energy, and they're all 5, so you can just count them down. Alright, so this is all about our lesson for today, and I hope it's useful. And don't forget that you can go down in the description and you can find the link for a quiz. It's not that easy and not that hard. It is a simple quiz. It's just an introduction for the lesson of the kinetic molecular theory of gas, and I hope it was useful. See you later.